This is a part 2 on a multi-part electrochemistry series that you can find on my YouTube channel, Chemistry Talks with Dr. T. And in this video, what we really want to focus on is working with galvanic cells or batteries. I want you to know how to be able to actually determine the voltage of a battery depending on what oxidizing reducing species you have. I want you to be able to define voltage, know what it really is, the symbol, know how it relates to fundamental charge. I want to introduce the Coulomb unit and help you understand what that means. I want you to know the relationship between cell potential or voltage and free energy, which we've talked about back in the thermodynamics section. I'd also like you to know how the voltage of a battery changes with concentration, and then finally know how to determine the cell potential of a concentration cell, a special kind of cell made only by changing the concentration in the anode and cathode solutions, know what species is which, and the conditions that the cell is that are driving it as it creates voltage. So let's just start with just a quick review about what we commonly call a battery, also called a voltaic cell or a galvanic cell. In all these terms are legitimate, they mean the same thing. The key is it's a redox reaction that takes place spontaneously, and we harvest the free energy from that reaction. So the parts that you need to remind yourselves about are that on one side of this cell you basically have an anodic compartment where metals are being oxidized, losing electrons. Those electrons build up on this electrode. On the other side you have a reduction event, which this is called the cathode, and in this case I'm showing you where protons, hydronium ions, are being reduced to hydrogen gas, and that requires electrons which are being driven over from the anode. And consequently, as you're losing positive charge here, because the hydronium ions are going away, you have to be replacing that. So you have to have something from the salt bridge to replace that. Meanwhile, the positive charge is building up over here on the anodic compartment, and so the salt bridge also has to replace that. So you might have sodium, for example, the positive cation in the salt bridge moving towards the cathode, and the negative, or the anion, in the salt bridge moving towards the anode. And often when you talk about these batteries, or you talk about redox reactions in general, you break up the separate reactions into two half reactions. So on one side we have the oxidation half reaction, and on the other side we have the reduction half reaction. And together, combined, if you compensate for the same number of electrons that are gained by reduction or lost by oxidation, you can combine these two equations together and get the overall cell reaction. So let's now connect this battery, which basically has a zinc oxidation with a hydrogen reduction going on. Let's correlate it with the standard reduction half potential table. And remember that these tables are laid out traditionally in reduction, every reaction done in terms of reduction and their corresponding voltage. And these represent half cells or half reactions. So talking about the reaction that just took place, we have protons changing over to hydrogen, and that is above zinc, going back to zinc 2+. And so what we've learned in previous videos is that if the reduction is above the oxidation, then that will happen spontaneously. But in this video we'd like to talk about the calculation and why that is. So here's the key equation, and I've got it circled because you need to understand how to use this. But you can always figure out the maximum voltage available from a battery, or the resting standard potential of a battery at standard conditions, by taking the cathode reduction, which in this case is the hydrogen reaction, and you subtract the zinc oxidation. And the beauty of this subtraction is it automatically accounts for the fact that this reaction is running in reverse, and you would change the sign. Well, you don't have to do any of that. You can plug it in directly as 0 minus a minus 0.76, and you basically are looking at a 0.76 volt battery from what we have diagrammed on the other page. So you need to commit this equation to memory. It's very straightforward. Remember, then you can directly plug in numbers from off the table without having to worry about whether you are switching the reaction direction here. It takes care of itself. Okay, and you'll get more familiar with that as you go on. The other thing you want to remember about these standard reduction half potential tables is they're laid out at standard conditions. So anything that's in the aqueous state is going to be at 1 molar. Anything in the gaseous state is going to be at 1 atmosphere. And all of these are assumed to be taking place at 298 K. And any adjustments you'll see in today's talk, I'll show you how to make adjustments for that with the Nernst equation. The other piece of this standard reduction half potential table is that the ones we use probably in this General Chemistry 2 class and you find in your textbook are relative, as you see here, to the hydrogen reduction as being 0 volts. But there's other standards that exist, and really this is based on solvent. You can't really do every reaction in an aqueous environment, so some of these reactions that take place, for example, in organic solutions might take a silver-silver chloride couple or a mercury reaction, and those sorts of things, the potential shifts accordingly. So it's all relative to some standard potential. There is not, there isn't, for example, like in temperature, an absolute 0 voltage. So it's always relative to some reaction. But you'll notice when you read these tables that standard 0 potential is going to be your standard that the table is set relative to. And once again, as I pointed out earlier, the minus anode, or where oxidation takes place, automatically accounts for the fact that the direction has switched. Okay, so for example, zinc being oxidized really is a positive 0.76 volts. But if you just plug this in as is, okay, from the equation itself, because of the negative sign, will automatically shift it for you. So this will work every time, and that avoids confusion. The other piece, when we did this kind of without trying to put numbers on it, I said, you know, reduction is above and left, the oxidation, which is down and right. And that's just a visualization for most of these tables. But not every table is laid out the same. You know, this is laid out by a potential when I tell you that the reduction will always basically sit above an oxidation. But you'll notice this is in descending voltage, and that's great if you want to pick a voltage, because now we know whatever the reduction is minus the oxidation. So for example, if I did these two together here, I could do 2.87 minus 2.07 and know that these two coupled together, with the oxygen being the oxidation and this fluorine going through reduction, it would have a 0.8 volt potential. So this kind of table is helpful if you want to fine-tune the voltage and you're not too particular about what the species are. But you can imagine there's another application where maybe you want to know periodic position. So for example, I want to look at two elements that are above each other on the table and figure out which is a better reductant or which is a better oxidant. Well, there are tables like this one which you'll look and see are really laid out by their position on the periodic table. So we're on the left-hand side, the first column, the first family, and you'll notice here's hydrogen, here's lithium, and you're working your way down sodium and potassium and on and on. That way you can just do comparisons. So for example, it looks like a lithium is a little lower on the chart. See, negative 2.92 volts than this sodium at negative 2.72 volts. So you can kind of compare those in terms of oxidation potential. Okay, another way that might be important is to just do them alphabetically, because now I'm concerned about a certain element. I don't know its voltage. I'm really concerned about the element itself. Well, of all the literally thousands upon thousands of elements you would have to search, you wouldn't want to find them laid out by voltage. You'd want to find them alphabetically. And so in that case, we've got tables like this that are all laid out alphabetically. So just pay attention to what table you have. And then as far as what we've been talking about when you're applying the rules, remember, the more positive the number, the more easily it undergoes reduction. The more negative the number, the more easily it undergoes oxidation. So for example, this 1.98, this thing could be the reducing agent over this 0.7996. So silver 2 plus going to silver would undergo reduction easier, the oxidation of silver to silver plus, just pulling 2 right off this table. So once again, regardless of the format, the more positive reduction potential will undergo reduction, with the less positive half reaction being the one that undergoes oxidation in a spontaneous reaction. Let's practice a little bit so you understand how this works. Let's say that you're trying to write battery notation and determine the potential, and sometimes we just write it the E naught. That basically means the standard reduction potential for a battery. And the two couples we have are iron 3 plus iron 2 couple and the silver plus silver couple. And so I'm not going to tell you which is which. You can decide that based on its location on the table. So immediately we go over here and we see that silver is above the iron 2 plus, so consequently the silver is going to undergo reduction, and therefore iron 2 plus would undergo oxidation. So in a standard battery notation, you always put, and I would refer you back to the last video if you don't know what I'm doing right now, but in standard battery notation, you basically would put your oxidation first, okay? In other words, your anode first. So iron 2 plus going to iron 3 plus, that's an oxidation. Then I'm going to separate that by 2 bars, and then silver plus going to silver is the reduction. This is change state, so I put a single bar in between there. These are the same state, so they would both be in solution, so they have a comma. Well, I'm going to have some sort of electrode to pick up the current from this event. And so I therefore would have an inert electrode. In this case, I'll use carbon, which is technically probably graphite. And then if I want to figure out the voltage, right? Remember, I take whatever's undergoing reduction minus whatever's undergoing oxidation without changing signs, and the formula itself will take care of that. And this battery itself would have a 0.03 volt of potential energy, or you might say 30 millivolts. All right? And I'm just trying to show you their position relative to how you use them in the formula. Always do reduction minus oxidation, cathode minus anode. So here's your chance to do a little practice. Build a battery. You're going to use a silver plus silver couple, and you're going to put it together with fluorine fluoride couple. I want you to decide which is which, give the overall equation, and then figure out the battery potential. So stop the video, see if you can solve this, set it up. When you're ready, restart the video and check your work. Okay, so let's see how you did. If you look, the fluorine's above the silver, so fluorine's doing reduction, and then the silver is actually undergoing oxidation. So you set that up accordingly. Like I said, traditionally in battery notation, you put the oxidation first, or the anode, followed by the cathode. So that's kind of handy alphabetically. These are in different states, so the silver electrode could be an active electrode itself, will conduct the current out of the oxidation. And then on the other side, to receive the current, because these are both, one's gaseous, one's in solution, you need something in there to make contact with where this event is taking place. So you need an inert electrode, and in this case, just to mix it up, I put in platinum. So hopefully you are learning that platinum and carbon are traditional inert electrodes we use. All right, and it's going to be 2 electrons for silver, so you're going to have to double up the silver. And as we learned in the if you look in the Appendix C video, the extra video, I kind of describe how you can do these balanced equations directly off the table. Long story short, though, you got to compensate for the exact same number of electrons. So if fluorine takes 2 electrons to undergo reduction, then it's going to take 2 equivalents of silver to do this. So now when you go to do the calculation, you do a reduction, 2.87 minus 0.8. And now take note of this. Although it took 2 electrons for silver to have enough electrons to drive this fluorine reduction, I do not make any changes in the overall potential. And you'll see as we go through this video where that comes back in. But for this original standard electron potential, you do not count for the fact that you had to double up. And this is a little different in thermodynamics, so that's why I keep pointing this out. Alright, so let's see if we can make this link between our cell voltage, our standard cell potential, and free energy. Because that's what we want to harvest, is actually the free energy. So in order to do that, you need to understand the Coulomb is actually a packet of electrons. Okay, 1 mole of electrons, remember 6.02 times 10 to the 23rd electrons. If I could plug them into one packet, a mole of electrons has a charge of 9.65 times 10 to the 4th coulombs. And a coulomb is that packet of standard charge. Now we'll talk about this in subsequent videos where as a coulomb moves by per second, that's what we commonly call an amp. That's a measurement we use. I'm not going to go into that a whole lot today because I just kind of want to stay focused on this idea of voltage. But anyway, this is Faraday's constant, 9.65 times 10 to the 4 coulombs per 1 mole of electrons. That's something you should memorize. So now what's the relationship with this and what we call the voltage? Alright, so we load it up, get all those electrons into the packet. So voltage is like a slope for that to make that charge flow. So once those electrons start flowing, we know that's actually current. But if you could imagine that those were flowing down this imaginary hill, it's just a good analogy to help you understand it. The steepness of that hill is what we call voltage. So it's the potential for that current to flow. Okay? And here's the key, the connection you should know. 1 volt equals 1 joule per coulomb. So in other words, that hill is steep enough to deliver 1 joule of energy for every coulomb if you're at 1 volt of steepness. So in my demonstration, I'm going to give it a 1 volt slope, and I'm going to move it down and do some work. And that work that I performed on that poor little penguin was 1 joule of energy I delivered to it to actually gently help it get back into the water. No animals were injured during the filming of this video. Alright, so for example, common US wall plug has 120 volts, cell phone has 3.8 volts. That wall plug is a much steeper, the coulombs flow with much more energy than the cell phone. So if I moved up to a 2 volt slope, you can imagine that that coulomb has a lot more energy. Just to kind of get that idea. So one qualitative way to think about voltage is it's the steepness of the hill down which current flows. Quantitative way to think about it is 1 volt is 1 joule delivered per every coulomb of flow. So here's the direct link that's going to get us from the battery voltage we know about, right? That's here, the E cell, back to free energy, which we studied in the past. You put a negative sign on it, and that makes sense because remember, so far we've been saying that look, if the E cell, if the battery has a positive potential, that means it's going to go spontaneous. Well, then you have to have the sign change to get it back to free energy, which we know if you have a negative free energy, things take off spontaneously. We talked about that in the thermodynamics section. So here's the N, and here's that connection I've been talking about. N is the number of moles of electrons transferred. So here's where it works back in that you can't compensate for, oh, I multiplied this equation through by 2. Well, that would mean 2 electrons are involved. Or if you look at the equation itself, it has so many electrons involved, that goes in N. F is the Faraday constant. It basically correlates the coulombs per every mole of electron. So let's just do a calculation here. let's go back to our fluorine to fluoride battery that we had just worked on. And we know that the E cell for that was 2.07 volts. So let's figure out at standard conditions. Again, let's look through this. That means when this fluorine gas is at 1 atmosphere, this fluorine ion, I assume, is probably in solution, so it's at 1 molar. And this silver ion is in solution, so that's 1 molar. The E cell on this would be 2.07 volts. So let's find the free energy. So you plug and chug. Now in this particular case, it was actually 2 electrons involved. Put that in here. Coulombs constant, that's always going to be the same, so that always fits in there. And then 2.07, and in this calculation, if you want to track your units, you automatically just convert volts to joules per coulomb, and then everything's going to cancel out, and you're going to be left with negative 399,510 joules, or 4 times 10 to the 2, or 400 kilojoules. Here's a chance for you to practice. A Voltaic cell uses chromium 2 plus couple and a tin 2 plus couple in the half cells. So you're going to have to decide which is undergoing what, determine the voltage, and then therefore turn it into the free energy at standard conditions. So we go up and we find, well, which one is the reduction. So that's going to be the tin 2 plus. It's higher on the table. Chromium solid is down on the bottom, so we can subtract these two, and that's going to give us our E cell. And once again, they're both negative, so just plug them in as is, and you see a 0.77 volts. The fact that it's positive means that we're going to have some free energy to work with. This is spontaneous. So we plug and chug. It looks like 2 electrons to make this happen in both cases. Plug and chug, and you get free energy of negative 1.5 times 10 to the 5th joules per mole. All right, now here's one for you to practice. I've got a cadmium 2 plus ion cadmium couple, nitrogen going to a hydrazinium ion, an ionic form of hydrazine. I want you to determine the free energy at standard conditions, and while you're at it, describe standard conditions. I want to see if you're ready to do that. So stop your video, see if you can solve this problem, and when you're done, restart the video to check your work. So let's see how you did. Nitrogen is above the cadmium, so we know that nitrogen's going to go reduction and cadmium's going to undergo oxidation. We just do a subtraction, 0.23 minus a minus 0.4. We end up with a 0.17 volt, so it's positive, it's going to be spontaneous. We basically plug and chug. Now this is interesting. If you look, in order for this to take place, 2 equivalents of cadmium to provide enough electrons to drive this reduction to the hydrazinium ion. So that's actually 4 moles of electrons involved. Plug and chug, solve this, you end up with negative 6.6 times 10 to the 4 joules per mole. Now it looks as if the moles cancel in this calculation, but I'm just trying to remind you that that's per mole of nitrogen that's reduced. Okay, so that just a good way to describe that. But that's also negative 6.6 times 10 to the 4 joules per 2 moles of cadmium that is oxidized. And that would make better sense if you drew the overall equation, and sometimes that's why you draw that to see what kind of equivalents are involved. When you describe the standard conditions, the cadmium and hydrazinium ion, those are both in solution, so those are 1 molar. Nitrogen's gaseous, so it's at 1 atm, 1 atmosphere pressure. And all the reagents are at 298 K. So now let's talk about what happens when you're non-standard concentrations. And I just want to remind you something from the thermodynamics section. Look, we talked about free energy at different concentrations. You had a standard free energy where everything was at standard conditions, very similar, 1 mole, 1 atmosphere. But what if the reaction proceeds and you start to change concentrations, or you start at a different concentration? So we know from doing equilibrium that you can incorporate the activity coefficient, Q, which actually will allow you to do the concentration at any moment, and key it back to the free energy. So there's an analogous connection there in what we're working with now for cell potentials. And this is called the Nernst equation, which basically says, look, you can take your standard E cell minus RT over NF, and we've learned we're going to use R as 8.314. That's the universal gas law constant. T is temperature, so now we get to incorporate temperature back in, so that's great. N is the number of electrons, once again. F is Faraday's constant, and then the log of Q. But we want to remind you again that remember Q as products over reactants, and raise those to the appropriate coefficients as needed. So we're going to do a calculation here just to kind of show you how this works. That if I was to take this chromium undergoing oxidation and tin undergoing reduction, we already have the E cell at 0.77 volts. And I'm just going to track this when I have these both at standard conditions of 1 molar and 1 molar. And I can look right here. See, here's the tin 2 plus concentration of 1 molar, which assumes then that the chromium's at 1 molar. Well, at that point, as we suspect, the actual E cell for that is going to be at exactly, 0.77 volts. So now, starting from that, standard conditions point, let's back it up. Now we're going to take the tin 2 plus and we're going to lower the concentration. So that means this actual reactant is getting lower and the product is getting higher. Okay, so the chromium would be increasing while this is lower. If you back that up, well, as you would assume, that means that this reaction has already ran out a little bit. As this gets lower and lower and this gets higher and higher, that means you've already gone towards products. So we're getting closer to equilibrium, and as that happens, you'll see the voltage start to drop rapidly towards zero. That's kind of the what it's approaching. Okay? But then if you go back forward and we go back to the standard conditions, and let's talk about the opposite. What if we overload this above standard conditions? So now it's not just, say, 1 molar, but let's just say that this is 1.5 molar and this is actually half a molar. So you can look on there and see that the voltage starts to raise. And that actually has a maximum on it as well. The way these cells run, as you go from reactants to products, right, this is going to be at a high concentration, and as the cell continues to run, this is going to lower. It's going to drive towards products. And we know that makes sense. You got a positive E cell. Should have a negative free energy. Consequently, you have a very high positive equilibrium constant. It's going to favor products. So this, you want to think through this a little bit. Spend a little time with this till you get comfortable with the idea that, the ideal for a battery is that you have a lot of reactants, and as the battery runs over time, it starts to flow towards products until it reaches equilibrium. And that point, there is no free energy and there is no cell voltage in a battery. Here's what I'd like for you to do. You now are going to use a chromium ion and a tin ion couple, and I want you to change the concentrations. Now we're not going to start at 1 molar. We're going to have the chromium 2 plus at 1.6 molar and the tin 2 plus at 0.2 molar, and determine the E cell at 298 K. And once again, you have to start by finding standard conditions and then use the Nernst equation to figure out where you're at. So we set it up again where we determine who's going to undergo reduction and set up our equation. We already know that the E cell is 0.77 volts. Now though, we find the Q. And the Q, if you look at the, and this is where it's good to know how to do the overall equation. That came in very helpful here, right? And we decided, oh yeah, the chromium 2 plus is 1.6, the tin 2 plus is 0.2. Whenever you're in this scenario, see your reactants are a little lower than your products, and that should consequently lower the voltage a little bit. So we do this calculation on Q and say, oh yeah, that's 8. Pull the Nernst equation and we just plug and chug. Okay? And sure enough, instead of being the 0.77 volts it was when these are 1 molar and 1 molar, it's actually at 0.74 volts. It's dropped a little bit. And remember, it's a 2-electron event. If you look at both of these, the one that uses the most electrons is the event. Well, let's talk about a cell that's different than this, where we don't have different metals, but all we've done is change the concentration. So over here on the anode, we have oxidation going on. Iron's going to iron 3+. Okay. And on the other side, we actually have reduction going on, where iron 3+ is going back to iron. So that would make sense. It would drive the electrons from the oxidation side, from the anode towards the cathode. And if you set up the equation, you would see that on one side I have the iron going to iron 3+. So if I was trying to do the Nernst equation on this, and I set it up and solve, the thing is the E cell here goes to 0, right? That there is no difference in metals because they're the same metal, so that disappears, and all you work on with this kind of equation is the negative RTNF log products over reactants, which I've made the note, the products in this case, right? That's the concentration of this, which came from this oxidation, or the anode, and the reactants are the concentration of this, which is actually converting over to the iron 0, so that's the cathode. And so this is the setup where you basically have anode over cathode, and now the question becomes, when does this thing stop running? Well, that stops running when the log of 1 becomes 0, and 0 times this quantity here will basically zero out. So it stops running when the concentration of products equals the concentration of reactants, i.e. whenever the iron concentrations equalize, that's when this will stop running. And just as long as you have a lower amount in the anode side and a higher concentration in the cathode side, this is going to start running until these equilibrate. And you can see that here as you follow the trend. We started off with the reactants in the cathode side being high at 4.5, and the products were at 0.5, and if you do the calculation, that comes out at a positive 0.018, or what we might want to say is 18.8 millivolts. And then you see as the reaction proceeds, the reactants start to drop, and equivalent, if I dropped a half a volt here, I'd pick up a half a volt here, so that would increase to 1. Redo the calculation. Now we're at about 1.2 millivolts. So do the calculation here. Now you're about 11.9 millivolts. See how this reactants is dropping, products is building. See how the voltage is dropping, and on and on and on. And somewhere along here, right, whenever you have reactants exactly equal to products, well, then the E cell drops to 0. And if you were to try and go past that, you basically would have a negative E cell, which is analogous to a positive free energy. So this no longer runs. This is a non-spontaneous situation. This is just set up on the Excel spreadsheet, but it actually doesn't run spontaneously. So this is where we kind of start to get the idea that A, whenever the thing's done running, concentrations are equal. B, think about what's going on. The concentration builds in oxidation and the concentration drops in reduction. Concentration builds on the anode side, drops on the cathode side, and the electrons flow from anode to cathode, and that all makes sense. A galvanic cell. We're going to take a strip of tin. It's in a 2.5 molar solution of tin sulfate. Take another strip of tin and put it in a 0.04 solution of tin 2-sulfate. Got to put in a salt bridge. That's the part that's back here I don't really talk about. As it starts, remember this is iron 3+, but it's counterbalanced by some counterion, so net charge on this guy is still 0. Okay, so you still have to have a salt bridge in here. Answer the following questions. What is the potential of the galvanic cell? Which solution acts like the cathode and which acts like the anode? We just talked about that in terms of concentration. And what will be the concentration of the two solutions when the cell is at a 0 voltage? So stop your video, look at this over, and see if you can solve the problem. So let's see how you did. First off, that's a bit of a red herring. You don't really need the half-cell potential tables to solve these kind of problems, because as long as they're the same metal, then the standard electron potential is out, and it's only done by concentration. So any metals that were put in this same situation, as long as the concentrations were same, the solution calculation would come out the exact same. So that's interesting. And really what really drives this, or why we'd even want to change solutions, is that's back to the early sections when we talked about solubility. And we know that some metals are more soluble than others, and that's what really drives the show on this. So what is the potential? You knock out the E cell and just work on the minus RT NF log of products over reactants. Plug and chug, we know that the products are lower than the reactants, and you come up with 5.3 times 10 to the minus 2, or 53 millivolts. B, what solution acts like the cathode and which acts like the anode? So as oxidation occurs, the concentration starts to increase, right? And while the other, the reduction side decreases, so you need 0.04 at the oxidation side, or at the anode, and the high concentration at the cathode. And then the concentration moves equal according to the balanced equation there. And we know that where they started, we just don't know where they end, but we do know that stoichiometrically, for every equivalent of tin that's reduced, an equivalent of tin is oxidized. So you can say, starting at a concentration of 0.04, as you start to gain concentration, the other concentration is going to lose the exact same amount. So you can always set these up and solve this 0.04 plus x equals 2.5 minus x. Solve for x, it ends up 1.23. That is not the final concentration, that's the change in concentration, right? So you can take 0.04 plus 1.23 or 2.5 minus 1.23, and they both equal 1.27 molar solution is where it's going to end up at. So I hope that this has helped you with these concepts, that you understand how to actually find the potential of a cell given a half potential table. I hope you understand, you start to appreciate what voltage is about, and we'll move on in other subsequent videos to understand things like current and power. I hope you understand how to figure out the free energy at any concentration in a cell, and also how to run a concentration cell and the direction the current moves.